Hello, everyone. Welcome to AWM Seminar. And our first speaker is Akshara Vincent. She's from the University of Pittsburgh, and her talk is Mappings Minimizing the LP Norm of the Gradient. Akshara, please go ahead.
Thank you, Roy, and thank you, everyone, for giving me an opportunity to talk in the seminar. So today I will be talking about minimizers of certain energy functionals, and I'll be talking about a theorem that states more about the regularity of these minimizers. So let me first begin with how this energy functional looks like. So let us define omega as an open bounded subset of Rn. And we look at a class of functions defined by set of all functions u belong to C2 of omega, such that u equal to the function g on the boundary of this set. So now we define the energy E of u as the integral of omega mod gradient of u square. So for this class of functions, we are looking at the energy E of u defined in this way, and we are looking at the function such that the function minimizes the energy on this class. Suppose this class has a minimizer. Suppose u be a minimizer of energy in this class A. So let's see what this minimizer satisfies. Let's try to compute the Euler-Lagrange equation corresponding to this energy functional. So for that, fix an arbitrary P belong to CC infinity of omega, that is the class of all sets test functions, that is C infinity functions having a compact support in omega. And for any real number t belong to R, if we define the map, define the function a of t by e of u plus t phi, we see that this function attains a minimum at t equal to 0. So that means a prime at 0 is equal to 0 because u is a minimizer. So that implies d by dt of this functional at t equal to 0 is also 0. Let's compute this derivative. So this is nothing but d by dt of integral of omega. So we have mod gradient of u square, which can be written as an inner product. Sorry. This is gradient of u plus t phi, gradient of u plus t phi at t equal to 0. Which is equal to t. We can take the derivative inside, and this is integral d by dt of gradient of u plus t phi, gradient of u plus t phi at t equal to 0, which can be written. So this is the derivative of an inner product, which can be computed as twice integral over omega, and then this is the derivative of the first term, which is gradient of u plus t gradient of phi times gradient of u plus t phi at t equal to 0. So now if we compute this derivative, this is nothing but integral over omega. The first one is gradient phi, and the second one is gradient u plus t phi. But when you evaluate at t equal to 0, this is what you get. This is by integration by parts, Laplacian of u, the negative sign, times phi. So we see that for any test function, we get integral over Laplacian of u, phi equal to 0. Since this happens for any test function phi by fundamental theorem of calculus variation, this implies Laplacian of u equal to 0. So the minimizer satisfies this Euler-Lagrange equation. So this is nothing but the Laplace equation, and it shows equilibrium of some physical quantity. For example, the heat in this room can be represented by the function u, and this represents that the temperature is at equilibrium, which is exactly when the energy is minimum at its minimum value. So this makes sense. Now, our goal is to look at the same energy functional E of u defined as before, but we change the range of this function. That is, you're looking at functions u going from a bounded open set omega to a unit sphere Sn minus 1. You can think at a unit sphere in R3, say S2. So we are changing the range and then looking at the same energy function E of u. Now let us try to compute what the Euler-Lagrange equation looks like corresponding to this energy functional with these functions. So assume for now we have enough regularity for the solutions to do the integral what we need. So as before, let us take a test function. Phi belong to C is infinity of omega. Now it goes to Rn, fix a phi. And then for any t belong to R, we see that u plus t phi may not go to the unit sphere, but if you divide it with the absolute value, it becomes a permissible function. And if you look at, if you define a of t as e of this function here, we see that if u is a minimizer, this function again attains minimum at t equal to 0. So as before, we have a prime at 0 is 0, which is nothing but the derivative of the function e of u plus dp by mod u plus dp at t equal to 0. Now we compute this derivative, which is d pi dt integral over omega. Now we have gradient of u plus dp divided by mod u plus dp, gradient of u plus dp divided by mod u plus dp at t equal to 0. We can take the derivative inside and as before we get integral of omega and then we interchange the derivative. So we get d by dt of u plus dp divided by mod u plus dp, gradient of u plus dp divided by mod u plus dp, evaluated at t equal to 0. Now here we apply quotient rule, so we get this is nothing but mod of u plus dp times the derivative of that, which is phi, minus the derivative of the denominator, which is u plus dp divided by mod u plus dp times dot the derivative of the interior, which is p times the first function, which is u plus dp times gradient of u plus dp divided by mod u plus dp evaluated at t equal to 0. So since we took the derivative, now we can evaluate the t equal to 0. So we see that I missed a denominator here. This is mod u plus dp all square. So the functions goes to the unit sphere. So absolute value of u is 1. So whenever t equal to 0, we see that all these absolute values become 1. So what we are left with is gradient of phi minus. So in this case, you have a u dot phi times u. And the second term becomes gradient of u, which is equal to twice integral over omega. The first one is gradient phi, gradient u. And the second term is minus the gradient of the second function, which is gradient of u dot phi u, gradient u, minus u dot phi, gradient u, gradient u. So now we see that if you look at the second term, this is the inner product with of u with gradient u. So if your function goes to the unit sphere, then you see that the vector u is of this form, and so the gradient u lie in the tangent space. So this inner product becomes 0. So we are left with twice integral over omega. We can apply integration by parts here. So what you get is minus 2 Laplacian of u times phi. And the last term becomes, so if you do the inner product, what you're getting is minus mod gradient of u square u times phi. So this implies minus 2 integral over omega Laplacian of u plus mod gradient of u square u times phi. This is equal to 0 for any test function. This implies Laplacian of u is equal to minus mod gradient u squared u. So our minimizers satisfy the Euler-Lagrange equation given here. So this is also called harmonic map equation. So this will be what we are going to look at. So first question that is interesting to ask is, why would the minimizers exist? Can we show the existence of minimizers? And the answer is yes, we can do that by direct method of calculus of variations. So existence of the minimizers is given by direct method of calculus of variations. So today, our goal will be to look at the regularity of these minimizers. So let me state the main theorem. Let n greater than or equal to 3 and let u belong to W1 to Bn to Sn minus 1. So Bn represents a unit ball in Rn and Sn minus is a unit sphere in Rn. Ba minimizing harmonic map. That is, take any B belong to W1 to going from Bn to Sn minus 1 such that V equal to U on the boundary of the unit ball. Then integral over omega mod gradient of u square will be less than or equal to integral over omega mod gradient of v square. That's the definition of being a minimizer. Then u is locally Holder continuous. Outside a set sigma such that hn minus 2 of the sigma is equal to 0. So what we say at, if you have a minimizer, then the minimizer is locally Holder continuous outside a set such that the set has host of measure 0 with a host of dimension n minus 2. So this is a result by Hart and Lin in this paper in 1987. So they actually proved the results for any mappings going from two different manifolds. So today my goal will be to explain this theorem by taking two specific manifolds, the unit ball and the sphere, and try to give the idea of how they proved this result and try to generalize this result to fractional suborder spaces. So before going to the proof, let us take a simple example. So suppose we are in R3. So our domain is the ball called P3 and the range is the unit sphere S2. So we are looking at mappings which minimize the energy as given there. So if you look at the simplest example, say u equal to x by mod x, this is a map going from B3 to S2. In fact, this is a minimizer of the energy functional that we have. So this is proved by Brisses. And as you can see here, so let's look at the regularity of this minimizer. So this function is continuous everywhere except the point 0. So the singular set sigma is nothing but singleton z0. So it overlaps, like it agrees with the result that we have. So the host of measure of the set is 0. So this is an example just to give a motivation. Now let's go to the proof. So the main this theorem is proved through main few different steps, and the first important step is the following proposition, which is called the decay estimate. So what does it say? It's like assume that let U be a minimizing harmonic map, as mentioned before, and fix any for any theta belong to 0, 1/2, there exists an epsilon greater than 0 such that if Bx0 R is a subset of the unit ball Bn and integral over Bx0 R to the power 2 minus n mod gradient of U square is less than epsilon square, then theta R to the power 2 minus n integral over Bx0 theta R mod grade U square is less than or equal to 1/2 R to the power 2 minus n integral Bx0 R mod gradient of U square. So what this proposition state, it says that suppose you have a small ball within our domain, say Bx0R, such that there is a certain bound on this energy here. This is similar to energy with the factor R to the power 2 minus n. If we have a bound on this energy, then what we can do is we can go to a smaller ball. So as you can see here, this says that if you go to a smaller ball, say theta R, the energy is still bounded. So that's why it's called the decay estimate. So suppose assume that we have this result for now. How can you use it? This is like an iteration lemma. So once you have assumed this result, suppose you have an initial bound on ball Bx0R, start with Bx0R, and you have a bound on energy, the result says that there is a bound on theta R. Now what we can do is you can choose a new radius R prime as theta R, and you see that this will be again because of the result here, integral over Bx0 R prime to the power 2 minus n mod grade U square. This will still be less than 1/2 epsilon square by assumption. So we can iterate this one to get that this is again less than theta R prime to the power 2 minus n integral B x0 theta R prime mod gradient of U square is less than or equal to 1/2 R prime to the power 2 minus n integral B x0 R prime mod gradient of U square. So we can do this iteration many number of times, and you can see that after k iteration, you can go to a smaller ball with radius theta to the power k and get a factor of k with initial radius r. So it's kind of like you are going into your energy is becoming smaller and smaller. So it's not surprising if I say that we can use this decay estimate to get a bound of the form supremum over, say, all y belong to Bx0 r by 2 and r belong to 0 r by 2 r to the power 2 minus n minus beta integral of byr made gradient of U square is less than or equal to constant depending on theta. So we use this decay estimate, iterate it multiple times to get a uniform bound over all balls around the point x0. So what is the advantage of having this bound? It's because of the following theorem, which is called the Campanatos theorem. Which states that let f be a function for some p greater than or equal to 1 and less than or equal to infinity. And suppose assume that supremum over p xr r to the power some constant minus lambda integral over pxr mod f minus average value of f pxr to the power p. If this is uniformly bounded by a constant lambda Then the function f is locally Holder continuous. So from the above step, we see that you have a bound on the gradient of the function. So we can apply Poincare inequality to get a bound on the LP norm of the function and then apply Campanator's theorem to get the desired result. So a clever use of Campanator's theorem gives us the result. That is, if we start with the point x naught and if we have a bound, energy bound, then we see that the function, our minimizer is locally Holder continuous around that point. So if we have decay estimate, we are done. If we start with the assumption, initial assumption that the minimizer has a bounded energy, a small energy around the point x naught. So what happens? What are we left to prove? We need to prove that what happens to the other points. Say we look at the other points x naught where we don't have such an energy. If we can show that those points belong to a set of measure zero, then we are done. So that follows from the lemma, the following lemma, which is also called Grossman lemma. That is, if you have a LP function in a bounded domain Rn and p less than infinity, and if you define a set E such that E is a set of all points x, where lim sub r goes to 0, integral to the minus alpha integral over pxr mod f to the power p, then h alpha of E equal to 0. So take all points x naught where we don't have a, from the decay estimate, we have the epsilon. So take all points where you don't have such an energy bound. Those points belong to this set, where f we take as a gradient of u, because the functions belong to W12, the gradient is a L2 function. So those points, by using this lemma, belongs to a set of measure 0. In our case, the alpha is equal to 2 minus n. So this proves our result, whatever we were aiming for. So initial result says that if you have a minimizer, we see that that minimizer is locally Holder continuous outside a set of measure 0. That completes our proof. So now the proof of the decay estimate follows by contradiction, which I'm not going to details now because of shortage of time. But now let me generalize this result to fractional subhollow spaces. So suppose assume that n is greater than or equal to 3 and let u belong to W, SP, Pn, Sn minus 1, Pa minimizing harmonic map. That means for any we belong to WSP of Pn Sn minus 1 such that v equal to u on the boundary of Pn. The energy, now in the fractional subhollow spaces, we have the energy defined by the integral this is less than or equal to integral over Pn mod v of x minus v of y the power v mod x minus y n plus sp dx dy. Then u is locally Holder continuous outside a singular set sigma with the host of measure n minus sp of sigma is equal to 0. So this is the result. This is a generalization of our local result to the uh, fractional subordinate spaces. This is based on joint work with Professor Shikora and Kasha. So we are trying to adapt the same result through this non-local results, and we are almost done, but we are still trying to improve our estimates on the variable S. So I think I'll conclude my talk here. Thank you.